Hello, this will be the last part in series of basic statistics. We will continue reviewing some basic MATLAB code to do some exercises to better explain things which we cover in the first two parts. So as you remember, in previous part we generate some simple distributions. We did different skew distribution, unskewing. We plot histograms. We also learn how to calculate z-score by hand and using MATLAB built-in function. We calculated size effect, and on the end of last lecture we also learn how to calculate statistical difference between two populations. So we had general population of heights of 100 students, and we had heights of 10 basketball players. And in MATLAB we can easily do it by applying t-test to function. We also learn how to do it by hand. So as we explained in first lectures, we need to calculate first distributions of means, and the p-value which we got from this was very similar to p-value which we got with this t-test. And the differences are because here with this doing by hand we are just doing some approximation. Here we are assuming Gaussian distribution, and numbers can be slightly different. Okay, so the basic idea that doing t-test by hand is that we were taking subsample from the general population of 10 people and looking what is the average height, and later distributions of those average heights we compare to average height of basketball players, and it turns out that it was very unlikely by chance to take 10 people from general populations that the average height would be as high as height of basketball players. Okay, so today we will continue this. And one thing what I wanted to also mention is difference between paired and non-paired tests. So here we have this distributions of heights, age of general population as we did before, but here we will generate another distributions that here from this distribution of heights we will subtract very small value for each person, slightly different value. So we will have second distributions of heights which will be slightly smaller. So you can imagine that this heights of these general populations were, for example, measured during morning, and as day progresses each of us is getting slightly shorter because tissue during day is compressed when we walk and carry different things. So at evenings our height is slightly smaller. So let's try to compare if the distributions of heights in the morning and distribution of heights at the evening of the same population is significantly different. So here we will generate the second distributions with slightly shorter heights, and here if we plot this histogram we will see blue for normal distribution, yellow for this yellow for normal distribution, and this blue for second distribution. So if we see that it's difficult to see any difference, both distributions are highly overlapping. So if we calculate this t-test, if there is any statistical difference between those populations, then the p-value of this non-paired test, it will be 0.75. So there is no statistical difference between both two distributions. But let's plot this two data sets in a little bit different way. So here we have what is the value of height for each of those 100 people, and if we zoom in, then you can see that there is two lines, blue and red. So blue, it is measurement during evening, red, it is measurement during morning. So what you can see is that there is very tight correlations between those two values, that high overlap between both distributions. But what you can notice is that as we design it, as by design, this red line is always slightly lower than blue line. So for example, this person, it was shorter in the evening by probably around 1 centimeter, it was only by few millimeters, and so on. So this red is, although that both distributions are highly overlapping, this red line is slightly below. And in such case, where you are doing repeated measurements from the same subjects over multiple days or multiple conditions, then it is often more appropriate to apply this pair test. So what pair test is doing is comparing not the mean of one distribution and other distribution, but rather is is calculating difference between this from each of blue points, is subtracting red point, and now is calculating what is the if this difference is significantly different from 0. So in this case, if we calculate this pair test, we will get that p-value is highly significant. It is 1.5 multiplied by 10 to minus 27, so it is close to 0. So basically what we are doing is that we are asking if distribution of differences, so h minus h2, if it is significantly different from 0. And as by design, because we subtracted some random number from each of those h values, so all those h values are bigger, and all those differences are between 0 and 1, so this distribution is highly different from the 0. So in t-test here we are testing if the mean of this distribution is significantly different from 0, and as we saw here, it is highly different. So think about it, about this non-paired and paired test, that because those two distributions are highly overlapping, we wouldn't find any difference, but probably applying this non-paired t-test is not the best idea. It's more appropriate to apply comparison how each person changed across days, to see if a change in height during day was significant, rather than this non-paired test. Okay, another type of tests which we covered during class, during first lectures, it was a randomization test. So as you remember, here for randomization test, we were assigning some random grouping for each of category, and calculated mean after this random assignment for each group separately, and we're trying to see how likely, just by chance, is to generate difference between two populations as the original one. And here is example, again looking at these distributions between general population and basketball players, so it is the same data, but here we will use this randomization test. So here to do it, we will create this one long vector of all heights. So we will concatenate H and B vector. So this is heights of general populations, B, this is vector with heights of basketball players, and we will create some appropriate group variable. So if I click here, and now I will plot group, what you will see again, because MATLAB is not very smart when scaling plots, so you see that what I did with this group variable, it is assigning group number 1, that all the first 100 people are in group 1 and the last 10 people are in group 2, and it is because the way how I concatenated those vectors, that first I put 100 people of general populations and on the end I attach 10 basketball players. So this is true groups of those people. But what I will be doing now in this loop, I will be randomly reassigning those groups. So here in these variables M1 and M2, I will keep what is the average for each of those random groupings. Here I'm generating some this R, it is vector with 110 numbers in random order, so it is this random shuffling of groups, and here I am applying this random shuffling of those groups to this our data. So if I plot now this group after permutation, what you will see, again, if this wouldn't be MATLAB scaling, that now person, for example, this around 25 was assigned to group 1, and so on, and the last 10 people are mostly in group 1 instead of group 2. So now I reassign those people to those random groups, and I will calculate what is the average height for this group and average height for this group. And I will do it 100 times such permutations and calculate such means of heights for this and the second group. And I will see how likely by chance is to get the difference between both groups in heights as big as original difference. So let's put this line in this code if somebody wants to execute, and let's put it as a star symbol, so it will be easier to see it. And here it is grouping of the original distribution. Okay, so let's execute this loop. So it will do this 100, and now each of those vectors M1 and M2, it contains what was the average height for first group and second group when we randomly reassign those groups. So here if I plot histogram, I will see that it is center around 0, that sometimes average of one group was bigger by 2 than the first group, but there was equally likely that average of the second group would be bigger than average of the first group by 2. So it is more or less symmetric distribution as expected. So now we can see what was the difference in height in original data, and it was 14. So now we can plot it on our histogram. So this is what was the difference in average height between general populations and basketball players. So basketball players were on average 14 centimeters higher than general population. But if we would take general populations plus basketball players and randomly reassign them who is basketball player and who is not, and calculate it what is the average height, the distributions of averages would be, it is shown here. So it will be very unlikely that the distributions would be at 14 or bigger. So again, this randomization test is doing something equivalent to this t-test, what we tested before. The one advantage of this randomization tests, as I mentioned before, is that we don't have to assume anything about distributions of data. So for t-test, we have to assume that distributions of height has normal distribution. Here, this method would work for any distribution. Okay. Another test what we were also mentioning during our previous lecture, it was rank order test. So here, instead of using actual values, we rank order those values and look if there is statistical difference between ranks. And what is good about this test, that again, it does not assume any, it does not need to assume a Gaussian normal distribution of data. One thing to keep in mind is that because of this rank orders, if, for example, last number would be not 75 but 5 millions, it wouldn't change the results, that the numbers, the values of the numbers are discarded, just only what is the rank in relation to other numbers, what is considered. So here I plotted some simple, made some simple code for exactly the same data. So in this example, we had number of book read by highly sensitive and non-highly sensitive students. So, I think that it was for example of I think I mislabeled this by history and English. I thought that this is example about numbers of classical CDs listened by history and English majors. Okay, so if we have this 4 different vectors, if we have 2 different vectors and they can be of different size, so in one group there could be many more numbers than in other group. What we can do is that now we can plot this data. So here it is what are the points in first group and in the second group, and here what we can see that MATLAB is again a little bit misleading when plotting it, because in this first group we have 2 data points at 9 and they are completely overlapping and we cannot see it. We only see 3 points. Similarly here for second group there are 2 points with value of 9, and again they are overlapping and we cannot see it. One solution to better visualize such data is to add some random noise to the data. So now what I did is that for each of those values I'm plotting it not exactly at 1 or 2. I'm plotting this with some random shift, and it allows me now to see clearly that for both categories there is 2 points with number 9. So here I was plotting things at 1 or second category. Here I'm plotting it at x1 but plus some random offset, and again here I'm plotting things at x2 plus some random offset. So how to do this rank test by hand? So what we can do is that we can just for example put in one vector this history and English majors, and now we have this one vector with both vectors concatenated, and unique comment function, it will change those things into scores. So if I plot it now, you can see that this unique comment converted it to scores. So 0 has this rank number 1, 4 is the second lowest number in this group, so it is converted to number 2, 36 is the highest number, so it was converted to rank 5, and if some numbers are of equal value, they will have equal rank. So unique comment is so now I can run this. So this is how we can convert things to rank. In MATLAB, we don't really need to convert this to calculate this rank order test by ourselves. We can just use this rank sum command, and it will automatically convert those scores to proper ranks and will give us value. So here it gave us value of p of 1, so it shows that there is no any statistical difference between both groups. We could also apply some t-test to those two data sets, and the t-test would say that p-value is around 0.6, so it's still not significantly correlated. And that example about those students was where it was. Oh, it was here. So the problem here was that because of this one student with value 36, this distribution is highly skewed, so applying t-test probably wouldn't be the best for that. Rank test would be better for this distribution. So we can also do rank test on both distributions. So here we converted this scores to rank test, and we will take the first 4 values and compare it to the last 4 ranks, and if we do it, we will again this value p1 that is not statistically significant. But if, for example, we will add 20 to this that English majors, it would be reading as much as history majors, but plus 20 more of those CD, then in this case this p-value will be significant. It would be below 0.05. So again, here is some simple example of rank order test that if distribution is not normal, you can use this command rank sum. If you would like to do this rank sum test by yourself, you can use this function unique to calculate ranks, and later either you can apply this t-test on ranks, or maybe even better it would be apply this randomization test on ranks or on original data. And there is quite a discussion in statistics community always which tests are the best to use, and it's not very clear. What I would suggest, what I try to do when analyzing my data, is to applying different tests. So in this case, I could, for example, apply this rank order sum test, but also apply this randomization test, and see if both tests are giving consistent results. If both tests are saying that data are not statistically significant in both groups, then it will give me more confidence that my results are not due to some particular test, but rather this conclusion holds regardless which test I use. So I think that reviewers usually like it when in the method sections you can mention that, oh, I also apply other tests for significance, and the results of these other tests were consistent with my main test reported in results. The last part of our lecture number 2, it was about correlations coefficient. So we were talking is that correlation is different from causations, that it only shows if there is some correlations between variables, but we cannot from this conclude what is causing what, that we need to cleverly design our experimental setup to answer these questions if one thing is causing other. But to calculate correlation coefficient, we can use function in matlab coef. So here I generate 2 random data sets. So how I'm making those 2 data sets to be correlated? Basically, I'm saying that the first variable, it is some variable with some random distributions, with Gaussian distributions, and the second variable, it is it is the first variable plus some random noise. So the second vector is not random vector, it is rather the first vector with some noise. So it causes that those 2 vectors are now correlated. And if we execute this, then we see that correlation coefficient between both vectors is 0.52, which means that this positive correlation, it means that they are related to correlated to each other. One thing what we also did is that we spoke that correlation coefficient is a very nice measure to find some relations between data, but is very sensitive to outliers. So here I will add a point at x20 and y minus 20 to this data set, and now let's see how this picture and correlation coefficient will change. So this is our initial data, and the new data point is here at x20 and y minus 20. And now if you look at correlation coefficient, it is minus 0.8. So it is highly negative correlations in this found for this data set. So even that if we zoom in here on this part, we see this strong positive correlation. This one outlier can really change what is the results. For that, it is always, as I mentioned, important to look at your data before applying such measure to make sure that it is not due to some outlier. And if you find such outlier, then you should examine it, why it is like that. And sometimes it is justifiable to exclude such outliers from analysis, but in such case, you need to clearly explain in method sections what points you excluded and what was the reason and criteria. Also, I mentioned that noise can affect what is the measured correlations between two variables. So let's say that here I have two vectors which are two variables which are completely correlated. They are exactly the same copy. So here G2 is equal to G1, so both values are identical. So the correlation coefficient between them is 1. But if I change that, if I add some little noise to the second variable, then now what you see is that even that those variables were perfectly correlated, if my measurement method is not perfect, if it is adding some noise, then the measuring correlations will be smaller. So here the correlation is 0.9. And one thing which I need to explain about MATLAB is that when I calculate this correlation coefficient, the first value is returning correlation coefficient. It is not returning 1 but 4 values. So how to interpret it? Well, this 1, 1, it means that it is correlation coefficient between G1 and itself. So G1, G1. Here it is between G1 and G2. This is between G2 and G2. So correlations between the same is 1. And here is correlations between G2 and G1. So it is the same as correlations between G1 and G2. So those are identical values. So this is in this matrix form, the results, and the reason is that you can give as an input to this Korkev function array, and it will calculate correlation coefficients between all rows of the array. And the second output of this correlation coefficient is the p-value. So it shows if the correlation is significant, and here it shows that correlations between the p-value is 0 between G1 and G2, so this is highly significant correlation. Here, because it is the same value, the correlation 1 for between G1 and G1, so it is just saying that this one, but that is the same variable. Okay, so this will conclude this second part of MATLAB exercises for basic statistics. If you have any questions, please do not hesitate to email me, and we can discuss in more details what tests should be applied in particular situations for in your project, and if some points of these presentations were not clear, we can also discuss it in details, and I can help you to better understand it, or advise you on some exercises which will clarify some of the topics. Okay, thank you.